This video is a part 1 of a complete CCNP Enterprise Advanced Routing course. Part 1 will cover IPv4 packet forwarding and DHCP for IPv4. Looking at this topology, PC1 and PC2 are on the same LAN. So what happens when PC1 wants to reach PC2 or send a packet to PC2? PC1 will first establish whether PC2 IP address is on the same LAN. So PC1, in this case, will determine that 192.168.1.2 is on the same subnet. At this point, PC1 knows that it does not need to send the frame or the IP packet to the default gateway on R1. Instead, it will send the frame directly to PC2. So the next step is, does PC1 have a MAC address for PC2? PC1 does not have a MAC address for PC2, so what it does is to send an ARP request asking what is the MAC address associated with 192.168.1.2, which is the IP address of PC2. At this point, PC2 responds with its MAC address, which is 222.222.222. PC1 has enough information to encapsulate the IP packet and send the frame to PC2. So how would the frame actually look? The frame will have the first part, which is the data and the transport. That could be either TCP or UDP. And then the part that is the IP header. So that's your source IP and your destination IP. In this case, the source IP is, of course, PC1 IP address 192.168.1.1, and the destination is 192.168.1.2. The source MAC address is of PC1 and the destination is of PC2, which was established after sending the ARP request to PC2 and receiving the answer. So what do we take from here is that when two hosts are on the same LAN, the default gateway does not get involved. Here we have captured some of the packets flowing between PC1 and PC2, and we are mostly interested in what happens with ARP request and reply. So at the top here, you can see the ARP request, which is essentially asking who has 192.168.1.2. At the bottom part, you can see that the target MAC address is a broadcast MAC address, and the sender is 192.168.1.1, which is PC1. In the next slide, we see the reply coming back from PC2. So PC2, using its address, is actually answering with its own MAC address. So sender MAC address and the sender IP address, which is 192.168.1.2. So this is essentially your ARP reply for PC1. And at this point, PC1 has enough information to create the layer 2 header and encapsulate the layer 3 frame and forward it directly to PC2. Moving on to a different scenario. Here, PC1 wants to reach or browse, in our case, server 1. As you can see, there are few routers in between the two hosts. So what would the process be? If PC1 wants to reach server 1, PC1 will have to establish the same thing as we saw earlier, which is 172.16.1.1 on the same subnet as PC1? Obviously, it is not. So PC1 knows that it has to send the frames or forward the frames to its default gateway on R1, and that would be 192.168.1.100. Does PC1 have enough information to create the layer 2 frame header? No, it does not. So what it does, it has to send an ARP request to R1 asking what is the MAC address of 192.168.1.100. R1 will respond with its MAC address. So at this point, PC1 can create the layer 2 header and forward the frame to R1. So from PC1 to R1, this is how the frame will look like. You will have your data, in our case HTTP, transport TCP, the source IP and destination IP. These two will not change in this process. So it will always be 192.168.1.1, which is PC1, and the destination IP 172.16.1.1. It is very important that you understand that in this process, the IP address of the source and destination remains unchanged. The only thing that will change is the layer 2 header. So as we can see, the source MAC address is of PC1, but the destination MAC is of R1. So now the packet is forwarded to R1, what happens? R1 receives the frame. R1 removes the layer 2 header and looks at the layer 3 header. TTL is reduced by 1 and the routing table is looked up. What happens if when reducing the TTL by 1 you end up with 0? Then the packet is simply dropped and an RCMP message is sent back to the sender. In our case, let's assume the TTL is over 0. So R1 encapsulates the packet in a PPP header because in this example, there is a serial link between R1 and R2. R1 has looked up its routing table and has established that it needs to forward the frame directly to R2. So R1 sends the new frame to R2. So how will the frame look like between R1 and R2? Same as before, the data remains unchanged, the transport remains unchanged, and the same for the source IP and destination. But instead of MAC addresses as we had earlier for Ethernet LANs or Ethernet links, we have a PPP layer 2 header. So now R2 will receive this frame. R2 does the same thing as R1. It will remove the layer 2 header and look up the layer 3 information. The TTL is once more reduced by 1 and the routing table is looked up. R2 established that 172.16.1.1 is actually directly connected. So R2 ARPs for 172.16.1.1, meaning that R2 sends an ARP request for this IP address. The server responds with its MAC address, which is 333.333.333. R2 adds the layer 2 header and send the frame to server 1. So finally, between R2 to server 1, data is unchanged, transport is unchanged, source and destination IP are the same as before. So essentially it's PC1 to server 1. The source MAC address is of R2 and the destination MAC address is of server 1. Now let's look at DHCP for IPv4. So in this very simple example, we have a DHCP client, a PC, a switch in between, connecting it to a DHCP server. It's very important to note that the DHCP server and client are on the same LAN. So how does DHCP operate? What are the steps and the processes? The client boots up and sends a discovery broadcast message. The DHCP server responds with an IP address offer. Now note that this is just an offer. The client accepts and formally requests the IP address. And finally, the DHCP server confirms the address is leased by sending an ACK message. So this is a 4-step process. First, the client sends a discovery, which is a broadcast. DHCP server responds with an IP address as an offer. The client accepts it and the DHCP agrees and confirms by sending an ACK message. Now let's look at something slightly different. The DHCP client is no longer in the same subnet or LAN as the DHCP server. The challenge that we have here is that routers drop broadcast messages. So when the DHCP client or the PC boots up and send broadcast messages, they will be received by fast Ethernet 00 on the router 1 and then dropped, which means that they will never reach the DHCP server, and therefore the DHCP client will never get an IP address. So how do we mitigate this challenge? The configuration that is needed here is under the interface facing the client sending the discoveries, and we need to add IP helper address 10.1.1.200, which is the IP address of the server. So what does this command do? When the client sends the discovery as a broadcast, the router now acts as a relay agent and forwards this discovery to the DHCP server, but as a unicast. So R1 becomes a relay agent, and the two-way communication can be established. And as a result, the DHCP client will receive its IP address. Now, let's look at what is needed to configure a Cisco IOS router to act as a DHCP server. So this configuration added to R1 consists in the following steps. The first thing that needs to be done is to exclude any range you need to exclude. So that will be hosts or devices which are, for example, assigned addresses manually and you don't want to include in the DHCP scope. The next step is to define a DHCP pool or scope. In our case, in this example, we have chosen pool NL_DHCP. And then we set the parameters such as a default gateway or DNS. In our case, we have chosen 172.16.1.100 as a default router. In the next section, we will run a demo lab where we configure DHCP in these three different scenarios and validate the outcome using packet capture on Wireshark. For this demo, I'm using EVE-NG, where I have two routers, R1 and R2, acting as clients, and I have a DHCP server. So note here that even if the icon used for the DHCP server, it's a server icon, in reality, this is a Cisco IOS router. The IP address of the DHCP server is 172.16.1.1/24. And no IP address on R1 gigabit 00 and no IP address on gigabit 01. But I do have an IP address on router 1 gigabit 01, which is 192.168.1.1/24. The first part of this demo is to see how DHCP works when the client is directly connected to the server. So in our case, what happens when R1 boots up and requests an IP address from the DHCP server or DHCP router as we call it here. So let's hop into our terminal. So at present, I don't have any configuration on gigabit 00 on R1. So as you can see, no IP address in here. The first thing I'll start with is to add the required configuration to support DHCP server on this Cisco IOS node. So the first two things that I will add is range of IP addresses I will exclude. So I'm excluding 172.16.1.10 and all the way to 120. And this, you can do it and you don't have to do it. All depends in which IP addresses in the range that you want to assign, you need to have excluded out of the DHCP scope. So your DHCP server does not lease addresses that are already being used by other servers or hosts. And then I will exclude a specific IP address, which is 192.168.1.1. This address is the address on R1 gigabit 01 facing R2. So I don't want my DHCP server to assign later on this IP address to R2. And now I'll start configuring my DHCP pools. So I'll start with a DHCP pool for R1. So the configuration is RP DHCP pool, and you name it. I'm naming it R1 DHCP. And I'll set the network that I want to have as a scope to be leased. So it's 172.16.1.0 and it's a /24. And then I will assign another pool for R2. So IP DHCP pool R2 DHCP. And this name you can choose for yourself. I'm naming them R1 DHCP and R2 DHCP, so I recognize which is what. So I'm setting the network 192.168.1.0 and it's a /24. But I'm also, in this case, setting the default gateway. This will become clearer later on when we do the second part. So this should normally be enough for me to start testing DHCP lease on R1. Now I go back to R1 and I want to set the IP address so it gets it from the DHCP server. But before I do that, I will actually start a packet capture here, so we can dive into what is happening in the process of DHCP. So I will capture on gigabit 00 on DHCP server. So going back to R1, I configure the interface so it obtains the IP address from DHCP server, and the configuration is IP address DHCP, as simple as this. So once I hit return, let's see what happens in the capture. I'll just stop the capture so we can dive through this. So the first thing you see here is the discovery message received by the DHCP server from router R1. So what we see here, the source address is 0.0.0.0 because R1 interface does not have an IP address yet, and the destination is clearly a broadcast. And then you get an offer from the DHCP server back to the client. So the source address is 172.16.1.1, and if you remember, this is the IP address on the server, and the destination address is a broadcast also. You can see the source and destination ports used. They are both UDP 67 and 68 for source and destination respectively. And then the client will have to respond with a request. This is when the client actually makes a formal request. It sees, first of all, that there is no, in the LAN, there is no conflict, there's no duplicate IP addresses. So yes, he's making the formal request to the server and say, yes, I would like this IP address. Source address is still 0000, and it's a broadcast. So let's just jump in here, see what happens under this DHCP request message. You can see the client MAC address, and this will be gigabit 00 on router 1. We'll check that in a moment. And you can see several options here for DHCP. So option 54 here, you see the DHCP server identifier, which is the DHCP server IP address, and the requested IP address. So this is the kind of candidate IP address that the DHCP server is offering to the client. Let's quickly double check this MAC address. So if I go to and you can see here the MAC address is the same MAC address used or seen in this Wireshark capture, which is the client MAC address. And the final step in this process for DHCP is the ACK. So this is when the DHCP server acknowledges and confirms that this IP address is formally leased to the client. So let's go up, and here we can see the client IP address. Earlier, something popped in the log message on R1, and you can see this message here. DHCP address assigned, interface gigabit 00 assigned, DHCP address 172.16.1.2, and the mask host is R1. So our IP address has been assigned by DHCP server to gigabit 00 on R1, as confirmed by here. If I come out and I do show IP interface brief, you should see here that the IP address is listed, as you would normally see it if you assign it manually, but here you see that the method is DHCP. So this is the first part of this demo. Now it gets more interesting. So we need to do the same thing but for R2 on gigabit 01. So the challenge here is once we enable IP address DHCP on gigabit 01 on R2, R2 as a client will normally send the DHCP discovery messages, but these are broadcasts. So once they hit R1, R1 being a router, remember that routers drop broadcast messages. So these discovery messages from R1 will be dropped. And the DHCP server will not hear from R2. So nothing is going to happen, and R2 will just keep on sending discoveries, and these will be dropped by R1. So let's put this to the test. If I go to R2 and I enable the address as DHCP, so IP address interface gigabit 01, IP address DHCP. I've closed the previous capture and I will open up a fresh one here. So what we need to configure on R1 to mitigate this issue with the dropped broadcast messages from R2 is a command that will allow broadcast messages to be forwarded to R2 as unicast. So essentially R1 will become a relay. So let's hop back into R1. And the command we're going to add here is IP helper address. And then the address that should be added here is the address of the DHCP server. So when the broadcasts are received, before I hit return, I'll just go back to the drawing. So once the broadcasts are received from R2 on this interface, gigabit 01, they will be forwarded by R1 to the DHCP server as unicast. Also, before we add anything on R1 interface gigabit 01, we need to ensure that this range, this subnet here, is actually known to the DHCP server. So we need to add a static route in this case to keep it simple for 192.168.10/24. So hopping back to the DHCP server, so I will add an IP route to 192.168.10 and it's a /24. And the outgoing interface is 00. So the route is pointing at this interface. Normally when you adding static route on a LAN environment, on an Ethernet environment, it is always preferred that you put the next hop IP address. But in this case, because this IP address is known by DHCP, it is not very wise to use a definite IP address because this could change in the next lease, for example. Or if I run the demo once more or renew the lease, I could end up with a totally different IP address. So this is the reason why I'm using an interface. So this in place here. Now I can go back to R1, add my IP helper, and check what's happening on the Wireshark session. So it took a little bit of time here, but as you can see, first of all, you can see that an IP address has been assigned to gigabit 01, and that's 192.168.12/24. Let's go back to the Wireshark session. So this is our discovery message here. But this is different from what we have seen earlier, where we had a broadcast. Here we actually have a source IP address. This is 192.168.1.1, which is essentially this IP address here on R1. So this is where the broadcasts are actually relayed from R1 to the DHCP server as unicast. The destination is the DHCP server. Going back to the offer, we can see that it's from the DHCP server to the router. So it's not back to the client, but it's to router R1 again. And the formal request, again from R1 gigabit 01. And finally, the ACK. So here I can see a MAC address for the client, which is the MAC address on gigabit 01, but on router 2. So as you can see, this is the MAC address here. So an interesting thing to check, remember that when we set the configuration for, let me just run the remember that when we set the configuration for R2, for the pool in R2, we did set a default router, which is 192.168.1.1, and this is the IP address of R1 gigabit 01. So the effect of adding this, if you go to R2 and you do your show IP route, you can see that a default route has been created and is pointing to 192.168.1.1. So to double check that we have connectivity here on R2, we haven't added any routing. We haven't added any static routing apart from this dynamic default route that was created when the lease or the IP address was assigned to R2. So let's see if we can actually ping the server, the DHCP server. And it's successful. So this is basically how you can configure DHCP on a Cisco router. So clients on the same LAN can receive IP addresses like we have done for R1, but also when the DHCP server is on a remote network. And we have also seen what needs to be configured when as in the case of R2, separated by the DHCP router by router R1, where you need to add the IP helper address command on R1, turning R1 into a relay agent effectively. So I hope you have found this session interesting and informative, and thank you for watching.